Um, awesome. So hello, everyone, and welcome to Panel to the People's Advancing Mathematics Communication panel. We're incredibly excited to have you as well as our amazing panelists joining us today. My name is Maya, and I'm an incoming freshman at Princeton University, planning on studying mathematics, and I'll be moderating the panel today. Our panelists today are as follows. We have Professor Arthur Benjamin, a professor of mathematics at Harvey Mudd College, author of several popular books, and prominent mathematics communicator whose Mathemagic videos have reached millions. And we have Professor Emille Lawrence, an associate professor of mathematics at the University of San Francisco, low-dimensional topologist, and advocate for broadening participation in the mathematical sciences. And we have Mr. Grant Sanderson, a YouTube content creator and notable mathematics communicator whose videos on the channel 3 Blue 1 Brown have been viewed over 100 million times. And we have Miss Mithuna Yoganathan, also a YouTube content creator behind the popular math and physics channel Looking Glass Universe, and PhD student in quantum computing at the University of Cambridge. And we put in some links that are relevant to our panelists in the chat. So while we're eager to hear the insights of our amazing panelists, we'll go over a few housekeeping items before we start the panel. First, we ask that you stay muted and turn off your video until the Q&A. You may use the reactions feature in the bottom toolbar for nonverbal feedback and enter any questions you may have into the chat. We'll try our best to address as many of them as we can during the Q&A. Awesome. And to our panelists, our goal here is to have a discussion rather than an interview. So we ask that you don't feel too restrained by the idea of having to discuss all of the questions that we've prepared for you. Our audience will likely gain more from a nuanced discussion of a few questions rather than a cursory address of many questions. So feel free to jump in and respond to other panelists' insights. We want to add as much dimension to the panel as possible. And with that, we want to thank our panelists and audience again for joining us today and proceed with the questions. All right, first off, could you give a brief overview of your involvement in mathematics communication and what math communication means to you? And Professor Benjamin, if you'd like to start us off.
Sure. Gosh, you know, I've always loved math, and as a kid, I also loved magic and just entertaining generally. So I think my goal in life was to somehow become some kind of entertainer. I did magic shows in high school, did in college. And then when I combined them with my passion for math and numbers and calculating, I found a connection that really worked for me. And not only in front of big audiences, but in the classroom as well. Just I learned a lot through performing about being a teacher. So one of my early idols was Martin Gardner, who wrote many popular books on mathematics and just engaged audiences through his writing, often through puzzles and games and magic. And in many ways, I've tried to follow in those footsteps. I guess the last thing I'll say is I'm no technological wizard, but I have fallen into certain things such as TED Talks, which have been viewed many times, and I'm an enormous fan of that kind of medium, like many of our panelists do, for spreading the gospel of mathematics. I'll leave it at that.
Awesome, thank you.
Is it my turn? So I would just say by far my involvement in math communication is communicating to my students as I teach undergraduate math at the University of San Francisco. So that's mostly how I communicate math. I like to think that I do it well. I certainly enjoy doing it. I wanted to be a teacher since as far back as I can remember, when I was maybe 5 or 6 years old. I'm the daughter of 2 teachers. And like Art, I've always loved math. I thought, solving puzzles, riddles, figuring things out. I've always been just very curious. And for me, I feel like math is a game, right? Just figuring out if I can make math play I like to try to work that into my math communication style. Having said that, I also give talks to large audiences. I've been a part of the National Math Festival, which is a day of math for general audiences. It's held every other year in Washington, D.C. So I was a part of that in 2017. I'll be a part of that again in 2021, which will be virtual this next time. So that should be interesting. So I guess I'll just close by saying I really enjoy communicating math. I enjoy seeing other people come around to math. That's one of my underlying goals when I'm giving a math talk.
Wonderful. Thank you so much.
Yeah, I kind of want to chime in to say, I actually, when I was younger, consumed a lot of what art put out. Like, I remember particularly lecture series about combinatorics and such. And that stuff actually mattered in terms of getting me a little bit more in love with the subject. And I think maybe that combined with certain other bits of outreach that I had seen in growing up and falling in love with it kind of seeded in my mind. I thought, like, this is, if not like a path to pursue career-wise, like something that's just worth doing, is if you love something, like trying to spread it. And I think I started getting into more of this just by playing with visualizations. I just really enjoy thinking about math visually and enjoy coding. And I think the tides were sort of right in terms of doing that in a way that could be shared more broadly. And YouTube was kind of matured around the time that I was starting with it. So for the last couple of years, that's been my main avenue of math communication. But I worked at Khan Academy for a little bit. I've partnered with some other organizations or contributed to places like Quanta or Udacity now and then. And in general, I'm just kind of leaning into the idea that if you broadcast it over the internet, it lets you have a completely different medium for trying to explain things just outside of a blackboard in a different way, and then also to a different like magnitude of audience than was possible before.
Great, thank you.
So just quickly, I do most of my maths outreach on YouTube, and the way that started was, yeah, I've always like loved all this like science communication stuff that I had seen growing up, but I hadn't really thought of like doing that myself. Instead, the reason I started doing YouTube was I was learning things and I thought it would be a good way to teach myself by making videos. So that's what I started doing. And then to my surprise, people started watching it. And I then it basically like shaped my like career as a physicist, because the things that I started making videos about, I started doing research in. So yeah.
Awesome. And I think those responses were very helpful in kind of formulating a more concrete conception on what math communication actually means to everyone and kind of how broad it is in scope. Awesome. So we'll move on to our second question. What would be your ideal implementation of math communication, and what are the biggest challenges you face in materializing this? And we could start with Professor Lawrence.
Wow. Okay. I don't know if there is one ideal. I have to say, I like the fact that on this panel, you've got people coming from different angles. So I'm sure I was not invited to this panel because of my YouTube content, because there is none. So for me, my ideal implementation is really in the classroom. I enjoy getting up in front of a class and teaching them about a new concept. I like to use visuals. I am sort of old-fashioned in the fact that I really do put chalk to blackboard, and I'm that person that just wants to fill up the blackboard with not only definitions and examples, but lots of pictures. So I'm a topologist by training. So when I communicate math to my students, I always try to find a picture or some sort of visual to put on the board. So yeah, that would probably be my ideal implementation. I will let other people on the panel whose expertise involves more technical things speak to that, but that's how I implement math.
Great, thank you for the insight. And we could go to Mr. Sanderson afterwards.
Yeah, well, I mean, right in response to what Professor Lawrence was saying, I think that it would be nice if there was a closer bridge between the sorts of outreach communication that happens through, popular books and talks and videos, and then what's actually happening on the ground in front of students, because it seems like there's, folks like me, I get to play by different rules of choosing the most inspirational thing and then leaning into it, but not necessarily going through the level of like detail that's demanded in a class, or the level of influence that you can have with that kind of depth and personal relationship with students. And I wonder what, like, if there's a perfect paradigm for math communication, it should be something where like the middle ground between those is a lot more filled out, where the people who are doing popular outreach do many more like series that really go into depth in something that can be paired together with classes, or that are associated with classroom activities and things like that. And it's unclear exactly what shape or form that takes, but if that's more on the minds of communicators, I think that that would make for just more engaging math in the future.
Great, and I think that makes a lot of sense. Yeah, we could go to Ms. Yoganathan now.
Yeah, so I think that like you guys have been saying, there isn't exactly like one best way to do it. I mean, there's different purposes. Like as Grant was saying, like one of the purposes of like the YouTube medium is to inspire people, whereas like in lectures, it's to be much more like focused on the actual content. And I think both are important. So like, I think one medium that I've kind of done some stuff in that I feel is like underexplored is doing things in classrooms. So there was a student group at my university that would go to like primary schools, meet with really young children, and we'd like teach them some abstract maths, and it would be fun, and it would be like hands-on. And something I really liked about that medium versus like YouTube or versus lectures is that you get the students to be able to do things themselves. And I think that that's a great experience for people, because it's not just like, oh, this is really fun, but also I can do it. So I really like that.
Wonderful, thank you.
And I'll just echo what's been said before. I think the ideal medium would be to have a professor like Professor Lawrence using video content like that of Mr. Sanderson and Ms. Yoganathan. I think you combine all that together and you'd have the ultimate learning experience.
Great. And that sort of speaks to one of the things that we're trying to explore with one of our last panels and this panel. So I guess we could pivot to this question, asking like, how do strategies used in math communication in general compare and contrast to those used in the classroom? And are there like specific approaches used in math communication now as a whole that you would like to see implemented in the classroom, or vice versa? We could start with Mr. Sanderson there.
Sure. So I get in the direction of like lessons from math communication taken to the classroom. I think on a place like YouTube, or if you're writing a book or something like that, you really have to focus on engagement, because you have a non-captive audience. And so there's this heavy focus on like, as you're introducing, is there a really compelling hook that makes someone wants to stay there? Or is there some endpoint that everyone's aware of and that keeps them wanting to come through? And a lot of professors and teachers and people in person do think about that. But if you don't have to, it maybe isn't as top of mind. The idea of like, what's the strong hook? What is the strong target point? Is everyone always aware of those? But then on the flip side, one thing that you can do in the classroom that I think those of us in more like remote media should probably take from is really actively encouraging, and to the extent that you can, enforcing students to do problems and actually do practice and things like that. And at the base level, this can just be that you have questions and open-ended things. Like this is one thing that Mithuna's videos do very well, is they have like homework in a sense explicitly at the end. And that's just taken from the kind of thing you might do in an actual classroom. I think you could probably go deeper, and you could have actual like practice problems associated with videos that if you wanted to extend beyond YouTube as a medium. The incentives are a little bit against that in terms of, what makes YouTube want to recommend things to people and such. But if you sort of are willing to transcend that, I think that's a common thing that good teachers do in person that maybe could be transported over to broader communication.
Ring coming up here. You must ring coming up here. And then they were like, oh.
Sorry about that. Yeah, we could go to Ms. Yoganathan in response.
Okay, well, yeah, I agree with a lot of what Grant said, but in particular, I think one thing that could come from Matt's communication into the classroom would be, as he said, like making it interesting to the students from the start, so they know like what the purpose of this lesson is, and then also giving a big picture. Like I think that that's something that I struggled with sometimes during like my maths education. You know, we'd be doing like this theorem, then that theorem, and the proof, and etc. And I wouldn't have a picture of like, oh, what are we going to achieve in the end? Like overall, what's the point of this subject and why is it interesting? And so that's something I'd love to see come into classrooms.
I agree. In every lecture I give, I try to have either what I call relevance or elegance. That is, the students should either see something that they go, oh, I could see how I could put this to use to solve problems that I'm interested in, or, well, this doesn't have to be useful, it's just so darn cool, right? And so it should have one or the other. They have every right to ask the question, when are we going to need this? And if the only answer is you'll need it in a later math class, then that really belongs to the later math class. If you can't motivate it right now, you know, then I mean, then you should reconsider teaching it in that course.
I'll just echo what everyone's been saying. I think those are great answers. If I could just add one particular thing is right now at least in the classroom, we're in a very specific situation where I would say almost everyone at this point is teaching their classes online. And we just started this week, in fact, and I'm teaching a stats class, like an elementary basic stats class, which I do not teach that class a lot. This is only my second time. But in a class like that, what I've realized is there's so much that you could sort of pull in from YouTube. So because we're all online right now, I've been supplementing this course in particular with a lot more content from the web, data sets from real life. All these things sort of make it come to life and sort of take it out of the context of, oh, we're just learning this just to be learning. What is the relevance, as Art said?
Well, can I actually ask, Professor Lawrence, is there something that you've been like looking for to help supplement the class online that's just not there, that like feels like an empty point for what actually helps someone like you run a class remotely?
Oh, that's a great question. Huh. I don't have anything that I've run into yet, but I'm guessing that you're asking because you might want to fill that void. Should I run across it? Could I count on you in a later time?
I won't say count on me, but you can send me the messages of pain points, and
Sure.
that'd be good to know.
So Grant, you take requests. That's great.
Wonderful. And to sort of echo some of the points that were made in some of the responses, we'll move to this question. So math can be quite abstract for many people. So practical applications often do serve as a bridge to the abstraction for the public. Have you experienced or do you foresee any limitations in using practical examples to convey mathematical ideas? And we could start with Ms. Yoganathan.
Okay. So my channel is very far from practical because most of what I cover is about quantum mechanics, and it's in particular about like the foundational questions of quantum mechanics. And actually, I think that there's a lot to be said for going on the other route and not going for practical things and instead going for the things that make people wonder and are like super interesting questions that you know you can engage anyone with. And then they realize that like that's the point of like doing maths research or like thinking about maths. It's like that you can actually find answers to things that, you know, matter. So I actually really like that approach. I know that the other one works as well, but like that's not one I'm really familiar with.
I have gotten a lot of mileage motivating problems through questions involving games and gambling. I just think people get inherently interested in it. And it can be a bridge to go off in all kinds of directions, whether it be calculus or probability. Like, here's a question I want everyone in the audience to think about. I'm going to do one just for 1 minute here. Imagine I gave you a magic coin, and not very magical, but it flipped heads 51% of the time, okay? And you're allowed to bet on that coin all day long. And all you have to, let's say you start off with $1,000, and at every bet, you have to commit to a fraction of your bankroll that you're going to bet each time. Okay, you could bet 1% of your bankroll each time, 2%, 10%, 50% of your bankroll each time. Your goal is to have the most money at the end of the day. What fraction of your money should you bet? Now, you don't want to bet 100% each time, because the first time you lose, you're broke and you'll have nothing. You'll have lost the whole $1,000. You can bet 1% each time, but maybe you're not going to make as much, in the end. You want to have a lot in the end. What's the magic number? Okay. And when I survey my classes, I see in the chat already people saying 10%, 20%. Those are by far the most popular answers. Okay. The answer is 2%. It's 2%, and that 2% comes from that 51% your chance of winning minus 49% your chance of losing. And that's your edge, 2%. Here's the scary part. If you bet more than 4%, more than twice your edge, by the end of the day, you will be broke. That $1,000 you started with will be worth less than a dollar. And that's amazing, right? So even though you have an advantage in this game, and to prove that, it's the world's best calculus problem, simple max-min problem. So all of you who enjoy calculus, I encourage you to do it. But anyway, I like to start off with something like that. And then I got your attention, and now you want to see the calculus. You want to see the probability. And my minute's up, but thank you.
I mean, that's such a good example where, like, I think all of us are very actively engaged there. And I think it's telling that when you were talking earlier, Art, about what you try to use to motivate people, you say, like, either practical application or something that's just so exciting. And that's the moment that we like see this emotiveness in your voice. Because it seems like a lot of mathematicians and the people who really fall in love with the subject, they care about practical application to an extent, but oftentimes it's something like intrinsic to it. And I think that when you have people lean too hard on the idea that the opposite of abstract is applied, rather than the opposite of abstract being like tangible and concrete in other ways, you can have really like awkward word questions that sort of seem very removed from anything a student would actually expect to see. That it's like the classic problems you'll see in the back of a middle school textbook. So yeah, more examples like this coin one that just like drive people in. I mean, I found that when people see pi in unexpected places, just universally, people love that, even if they don't usually like math. And that's a totally non-applied situation, but it somehow strikes a chord within us.
I was so captivated with Art's example. I'm not sure what the question is anymore, but I will just piggyback. I think it may have been about motivating. I like to use maybe examples that people have never thought about to motivate advanced topics. So one example I have in a topology class that I teach every so often is I'll say, okay, think about all of the letters of the alphabet and draw them on your paper, capital letters. Now, if those letters were made of rubber and you could move them around and mold them, which letters would be the same in this way? So the students start thinking maybe like, oh, if I write a capital C, if I could move it around and bend it and shape it, maybe that's the same as a capital L. And then, oh, well, maybe that's the same as a capital M because it's all just one line. Maybe that's the same as capital N. Okay, but what might be different would be the capital O, right? So that's sort of intrinsically different from the other examples that I said. So what I'm doing, I'm using a simple elementary school, if this was made of Play-Doh and you could move it around, to motivate a topological equivalence, right? So people tend to like that example.
Awesome, thank you all. Great, so starting with Professor Benjamin, we'll move to our next question. What false preconceptions do you think the public has about mathematics? And what have you encountered as the most powerful way to dispel such assumptions. I think you're on mute.
Yeah, boy, there are so many. I think starting from the feeling that there's some sort of a math type, a math gene, that you're either good at it or not good at it. I really do feel that math is a skill and a craft, and anyone can get much better at it. I may not have the potential to become a concert pianist, but I could get okay at playing the piano if I really put my time and effort into it. And there's some things that I might gravitate towards a little better than other things, but I really think that that with math, if you put in the time and effort and seek the right resources, that everyone is capable of doing it and enjoying it. My message to the students out there in the audience who are suffering with a terrible teacher, maybe in elementary, middle school, high school, college, and you say, I hate this stuff, please don't let that teacher, that one bad experience, derail you for what could be a lifetime's worth of value. Math is just so important and so wonderful when you understand it. And it opens so many doors that you don't want to give that terrible teacher or experience the power to ruin more than that 1 year of your life. And if you feel like you have to get back on track, find a tutor, find resources, and get back on, because it's just so important. I'll stick with that one example.
I might be out of turn right now, but I just want to piggyback on what Art just said. It is so important that students out there know that there's not just some group of people that hold the keys to all of mathematics, and that they don't have access to mathematics. And I think what he said is exactly right. People are sometimes turned off to math because maybe they had a bad experience early on. I see that happening all the time. Someone says, oh, my middle school teacher didn't encourage me, or my high school teacher didn't. But don't let that sour you on the idea that you can do it, because you can. Everyone can do this. And it is hard. I won't lead you astray on that part. Math is hard, and math is hard for every one of us. But everyone has access to mathematics. So I'm always preaching the gospel of mathematics for all. And another important point that I want to make is that it's not always because of a bad teacher, but it could also be because of who we see teaching math. Who do we see in front of the classroom? If you go back and you think about your mathematics teachers in high school, middle school, even elementary school, especially in college, what are the faces that you see? Do they look like you? Are they women? Are they people of color? I would guess not a lot, not a whole lot. So that is another thing that could demotivate a student to saying, I can do it. You know, I don't see myself in front of the classroom. So I think it's so important to lift up all voices, all communities, all colors, genders in mathematics, so that there can be more representation in math, and people can say, well, I see myself and I can do it too.
I just want to chime in saying I think this is a hyper important point, that like one of the main conceptions people have is that there exist math people and then there are not math people. And you tell someone you do something related to math, they're like, oh, I hate that subject. I'm not a math person. I'm curious to just hear other people's thoughts on why that's the case with math more than it is with other things. Like, I never see this in the same context, even with science, much less other subjects like art or literature. You don't have people saying like, oh, I'm not an art person, or I'm not a literature person, with the same sort of visceral reaction. And I have my own thoughts on like why this might happen with math more than other things, but I'm curious if like others have like have guesses for what's going on there, so that we can think about how to directly counteract like the underlying cause.
So I think Grant and I might have talked about this before, but like I reckon one of the reasons you get that reaction with maths so much more than any other subject is that you get tested on your maths ability so early in life. And like unlike any other subject, like you don't get like tested to see if you deserve to go into the higher streams of maths at like English or like, you know, history or something when you're 13. Whereas like you do for maths. And so my experience was that when I was in high school, like I didn't really like maths. And so at 13, like I got basically put into like one of the lowest bands of maths. And I just like, you know, was like, oh, that's fine. I'm just not a maths person. Like that just means I just don't have the maths gene, and that's no problem. So it was only like much later in life when I went to university and I was studying physics that I happened to like stumble into like some abstract algebra class, and I was like, oh, this is amazing, and it looks so much different from high school. I think it was because it looked a lot different from high school. I wasn't like so worried that like, oh, this is like an equation, I can't solve equations. Like it was a lot easier to go in because there wasn't as much stigma around like actual pure maths versus the kind of maths you do in high school. But most people only see this sort of stuff you do in high school, and that stuff is like very like, you know, you just have to drill, you just have to like learn how to do that stuff. And some people, you know, have a bit of a head start, or they're a little bit quicker at it, and they get told that they're the only ones who can do it. And I feel like this doesn't just happen in that many other subjects.
If I may add one more thing, I think that you know, one of the things about math that people either love or hate is its exactitude, right? That is, at least in the early stages of mathematics, there's one right answer and you can't bluff your way, and it's either right or wrong. And some people are drawn to that, like, good, you know, I have the right answer. No one can take that away from me. It's not subjective. Others, you know, say, oh no, now I can't bluff my way through this. So I think it's the other thing that I think misconception about math is that math is a disciplined subject. That is, it's about solving that equation, doing that calculation correctly, and math is an exercise in disciplined thinking. If you follow these steps, you'll get the right answer. Whereas I think it really should be seen as an opportunity for exercises in creative thinking. How many different ways can you solve this problem, right? And that appeals to another kind of person. So I think the creative aspect of mathematics is not seen enough in our classrooms.
I think the analogy to sports should be drawn. Oh, sorry, don't want to talk over.
No problem. I'll just quickly echo what Art just said, because it is really important. I think the way we start teaching mathematics early on is, you know, solve for X. You know, how do we solve this? Processes, methods, instead of the creativity, the artistry. You know, math is beautiful. Do we ask students to notice math in nature? Probably not enough. Probably not enough at an early age, certainly. Recognize patterns in nature. So all these things, if they could maybe be brought in at second grade or from the start when we start teaching mathematics, I think people would have an overall better perception of mathematics as a subject in general.
Yes, and so sort of leaning more into that, and this was discussed a little bit already in the responses, but how do you currently reach out to audiences that have a negative or weak background in math, and how do you think this outreach can be, if at all, improved? And we could start with Professor Lawrence there. I was just going by the order, although that got kind of, okay.
I think what I do is I try at least to just bring things down to earth. Okay, so as I said, I mostly communicate math in the classroom to undergraduate students. And I take hard concepts and I might give a definition, a technical definition, and an example. But I like to sort of then say, okay, but that's the technical definition and this is how I think about it, because those two things are very different. So I guess that's what I mean by bringing it down to earth, speaking in very plain language, giving relatable examples, drawing pictures so that people can see what's happening. Because I would say, if I get a class of 30 students, probably 10 of them or more will have a negative feeling or an anxious feeling about math. So what do you do when someone is anxious? You calm them down. This is not that bad. This is really what's going on. This is how I try to communicate the ideas that I'm presenting in class.
Great. And anyone could jump in, but going by the order, we have Mr. Sanderson next.
Well, so I think it's telling that you have this contrast between when you said, Professor Lawrence, like there's the way it's technically defined, and then there's the way that I think about it. And I actually think this is a little bit of it's like a cultural disease in math texts and formalities that's not present in like computer science and physics and other technical fields, where it feels like the standard way to teach it, at least a lot of how I was taught as like an undergrad, you have the axioms that you start with and like the formalities that you start with, and then you have the theorems, then you prove the theorems, and then maybe some examples at the end. And then there's this big difference between what the axioms are encoding and like the motivation for why they're encoding that. And it personally took me a long time to realize that those axioms are actually an end point and not like the starting point. Even just in the historical development of fields, you have people really non-rigorously studying something like Newton and Leibniz with calculus, who had no conception of like epsilons and deltas. They just were thinking in terms of infinitesimals and much more intuitively, but in a kind of rigorous way that could help them solve problems. And it wasn't formalized until like Cauchy and Weierstrass and such. And then it's weird that we have this reversal in how we actually teach it. And I think the more people who approach it like the way that you do, where you're saying, here's how I think about it. Or I saw like a question phrased on Twitter the other day that was very wonderful. That was like, what is a normal subgroup morally? Like this idea that there's a difference between what something is technically and what it is morally. And like what that prompted in terms of like answers was really good. And the thing is, we actually see this, I think, if you go to computer science textbooks or blogs that are trying to teach people about algorithms and things like that, there seems to be a culture there around motivation and around starting with something that's fuzzy and not precise, but then getting into a precise form. And maybe it's because in that context, it's known that you're going to get to the precise form because you have to have code that runs by the end. But maybe in mathematics, we're a little bit uncomfortable having at any point of our explanation something that's not technically true. And just like throwing in one other example of like a contrast between things being done like particularly well and particularly I won't say not well, but something that sort of closes people into a different mentality. Like if you try to learn math from Wikipedia, there's something impenetrable about it if you don't already know the topic. But if you go to something like, even if it's like a higher level thing, something like the Princeton Companion to Mathematics, where it's articles written about a given topic, but by a single author, like the single author often has this fluidity to say things that are slightly wrong at first and then crystallize them later. And I think encouraging students to recognize that there's a difference between types of texts out there. There's the ones that have this stable point of everything's exactly correct. And then the ones that have a stable point of narrative flow given by a single author, and like offering them some guidance on not feeling totally despondent if they're in the middle of a text that doesn't make sense to them. Because the reality is like, it doesn't make sense to a lot of us at first. So that's not a reason to feel bad.
To borrow an example from linear algebra, I mean, if you've taken linear algebra, sometimes they hit you with a dozen axioms of what a vector space is. And I like to say a vector space is like Las Vegas. What happens in the vector space stays in the vector space. You know, you add things in there, you multiply it by scalar, it stays there. And then that's what they remember, like for the course. It's like Vegas. Yeah, V, don't think of it as vector space, think of it as Vegas. And you get a lot of mileage out of simple statements like that.
Okay, so to answer the question in a slightly different way, because I agree with everyone that maths needs to become way more approachable in the content itself. But I think like, I don't know, another thing that you should be focusing on is how we talk about maths, like how we talk about the kind of people who can do maths, and like how we talk about, you know, getting it wrong versus just like, you know, figuring it out. And so one thing I tried to do with like my maths outreach is to talk a little bit more about like how maths was a struggle for me, and when I learned something new, like all the sort of dead ends that like can happen. I think those are really interesting for people, and I think it shows that, like, you know, no matter like how advanced you get in mathematics, like it's always hard and it is always a struggle, but that's actually like the fun of it. I think that's important for a subject like maths that usually gets portrayed as about being right.
Could I take one moment to piggyback on what Mithuna said? I actually co-edited a book about the struggles that we all have in math. I'm sorry, Maya, I did not send you the link to this because I'm just thinking about it, but math is hard for everyone, exactly like she said. And this book is called Living Proof, and me and Allison Hendrich and Maddie Ponce and Dave Taylor co-edited this book, and we got essays from mathematicians from all walks of life to contribute about their own personal struggle story with math and how they overcame it. Oh, maybe this is in the chat right now. So it's free and available to download from MAA's website. So I suggest that everyone check it out. My own personal struggle story is in that book, and 40 other struggle stories are in that book. So if you're looking for some inspiration, it's not just you that might have some struggle with math.
Awesome. And I think these are all wonderful points that were brought up. And that kind of harkens back to, you know, what math really is fundamentally, which at least for me is understanding things and making mistakes along the way and then contributing to that understanding in sort of snowball effect. Sort of like Feynman's approach, kind of making things as clear as possible and focusing on understanding. So I guess for one last question before we pivot to taking questions from the chat, to everyone really, conveying mathematics through a visual approach has been celebrated as an especially effective method for broad communication and comprehension. Do you anticipate any limitations, or can you suggest any improvements on such a visual approach? And we could start with Ms. Yoganathan.
No, I really like the visual approach. Not sure what limitations it has besides the limitation of it being passive, which is, you know, inevitable if it's sort of like online as video. But like as a video format, I think that making it visual makes it so much more approachable. And like I'm sure everyone here has had this experience watching Grant's videos where like there's some complicated topic and then there's some like beautiful visual and it's like, oh, I get it. Like it just makes it so clear. So I love that. I think that the only thing that I would maybe add is like maybe more interaction so that you can like play with the visuals, which is something again that Grant has been like looking into. So yeah, maybe Grant, do you want to say anything about that?
Sure. Well, maybe heretically against like what I do, I would offer some pushback against like the power of visuals in teaching math, where like in two ways. One is sometimes you find that you want to describe something without the formula. Like, okay, the formula makes it seem more complicated than it is. Here's the pure visual, and you explain it, and then everyone nods along. They're satisfied, like, yes, I understand it. But it might actually be more pedagogically beneficial to use that visual to motivate the formula. So let's say you're doing something like, why is the surface area of a sphere what it is? And there's kind of two ways that you could go at it. One is you teach someone about surface integrals, and it ends up being like a more basic kind of surface integral, and you parameterize the sphere, pops out of the formulas, you're integrating sines and cosines. People are snoozing already. The other way is to go with like the Archimedean proof, which is really very beautiful, where you imagine this cylinder encompassing the sphere. You're sort of projecting light out from it, and you're understanding why there's this correspondence between tiny bits of area on the sphere and on the cylinder, and it's something you can unwrap. And so it gives you this wonderful feeling. But and I'm saying this hypocritically because I made a video about this and I didn't draw a connection. I think the best way to do that would be to then let that whole thing motivate surface integrals, which in reality are a much, much more powerful tool, where often when you're applying them, there's not the same like beautiful Archimedean thing with it. Also, it generalizes to things that you'll never be able to visualize, like doing the analog in 5 dimensions or something, but which might actually be very useful. So sometimes I look back at stuff that I've made and feel like a shortcoming is not drawing that connection tightly enough. And also kind of sending the implicit message that what real understanding looks like is to have like a strong visual, which I think can, at least for me, like this can actually be a blocking point to progressing in learning a subject, where you're reading through some book and you're like, oh, is there a nice clear picture I can have for this in my head? And when there's not, you just get stuck and you don't proceed forward. But I think it's a really valuable lesson for people to learn, to understand how you can put a little asterisk around that topic and say, I don't have the picture yet. I have a different understanding. Maybe that's enough. Maybe I'll revisit it, but it's okay to move on without that. But then also echoing what Mithuna said about like a level of interactivity might actually really buff this up. And so I think Desmos is one of the best like companies and products out there, because it's not just that you're able to quickly visualize like functions with graphs and such, but they have a level of really immediately making it something that you can interact with and tweak and play with. And if you as an educator are sharing the topic that you're teaching through a Desmos graph, anyone can just touch it and like alter it themselves, which I think can be a very powerful idea. And we're not quite there with visuals more broadly, and it's actually a really hard thing to do with more types of things. I can speak more to like some experiments we've tried with that, but it's worth doing, but it's clearly an extremely hard problem to actually get that fluid ease of interactivity that doesn't end up feeling clunky on any of these things.
I have nothing to add. That's great.
I'm not sure which direction, if you wanted to go in this direction, but I'm going to give an answer that came to my mind. I too love using visuals, graphs, and pictures. But right now, this semester, for the first time, I have a student who is unable to see. And so I am sort of being pushed in different directions. How can I convey this visual that I have on my slide to accommodate my student who cannot see this? So it's sort of making me blow up the box and think about different ways to communicate my visual. So that's just something that I'm sort of pushing up against this semester, is to make it equitable for everyone in my class.
That's wonderful. And it also serves as a wonderful segue into one of the questions we did receive in the chat earlier. And it asks, are there any suggestions for communicating math to English language learners at all levels? And anyone could jump in on these.
Maybe I don't understand the question exactly. Like translating content seems like an easy way to go in terms of making sure that things that are made, it's also, you've got subtitles or to make it more accessible. Maybe actually like using simpler language, it shows that that's a benefit in 2 different directions. One is it forces you to say what something actually is rather than the technical jargon around it. But maybe if all of us are cognizant of the fact that, if you use only the 1,000 most simple words, then it makes it a lot easier to understand for English as a second language. That might be a helpful forcing function.
All right. Anything else to add? So I guess then we'll move on to another of the chat questions. So let's see. What do you think of the trade-off between learning foundational math and application? For example, many libraries in computer science use calculus, but do not need to know very much calculus to use the library itself.
Sorry, can I clarify what that question was? Was it the trade-off between learning foundational maths and learning useful maths, or what was the?
I believe it's just talking about application and like.
Oh, okay, sure.
Yeah, versus foundational math.
Okay.
I guess I do wish that students at all levels, maybe beginning in high school and throughout, had more flexibility in pursuing the kind of mathematics that would most appeal to them. I mean, I think after you've gotten to arithmetic and algebra, you actually can let students go a certain way, just like there's no universal path to mastering music or other art forms or sciences. I think we could be a little less rigid in our pyramid of algebra, geometry, trigonometry, calculus, more calculus, you know, abstract mathematics. I mean, you just lose so many people along the way. And I just think we're victims of tradition that so many people are afraid to break from, at least at the pre-college level.
Wonderful. And here's another one. So I guess in undergraduate level math, you tend to get introduced more into proofs rather than just working mechanical things or just understanding concepts. So someone asked, how can we create a more innovative or creative mindset in math communication that sort of, I guess, emphasizes more of that reasoning and proof-based thinking?
You know, I'm a big fan of the problems that come from contest math, where I'm not as much a fan of the time restraints put on the tests themselves specifically, or the implications of like we have some winners and some losers. But if you just isolate it for the problems themselves, it's an incredibly good bank. Like if we just go across all of the, you know, the AMCs or the tests in different countries leading up to the IMO and such, we have just an unparalleled bank of really creative questions that bring out alternate ways of doing things. And I think trying to bring those in more context can actually do exactly what you're commenting on here, is making people appreciate this sort of more creative approach to things, but in a way that has an exact answer. It's not creativity in a total sandbox where what anyone does can be correct. There's actually something really satisfying about knowing that an alternate perspective on something that you came up with that your peers didn't led you to the correct answer, and maybe it led you to it in a more elegant way. So if we start thinking of contest math problems not as just being for like the mathletes or the like top of the class, but instead just as this wonderful bank to draw on that we can go through like as slowly as we want to, I think that like the hard work has already been done of creating them in the first place.
Yeah, and I think certain like application problems in classrooms could do a similar thing where there's two parts to it that you need to do. Like the first part is formulate the precise version of the question, which I think is super important when you're actually doing maths. Like no one tells you the theorem that you want to prove. You need to like figure out like what is the interesting question here, and like what are the assumptions that I want to put in. And like that's a skill that's just like completely neglected, I feel, in high school level. So that's like important. But then also, like Grant was saying, you have now a precise question. You need to try and figure out the answer. And the method is not just some method from the textbook. Like you can't just follow like step A, B, and C and get the answer. And like there are many different ways to do it as well. So I think that showing like these kind of questions can help people realize that firstly, like maths is applicable to many things and understand how to do that sort of mathematical reasoning to make things rigorous, but then also appreciate that like you can solve a problem many different ways as long as you're following these rules of being rigorous. And I think that was something that was like quite a revelation to me when I first started doing maths in university, because I was like a very loose thinker. Like I'd be like, well, if that feels right, then this is right. And it was like great for me to go to my first like analysis class where it's like, no, like you need to prove that, you know, like all these really basic statements. So I think like teaching that kind of thinking can really help with people's thinking in life in general. And so I think it's something that's super valuable to be done at high school level.
Of course, to be able to do it at the high school level, you need to have teachers who themselves are well-versed and enthusiastic about that approach. And I fear this is somewhat of a, I don't want to call it political statement, but that we don't value our teachers enough, and we don't make it a respectable enough, high pedestal enough profession to attract the real stars and real lovers of math to enter the teaching profession. And if you you can't expect a student to be more enthusiastic about the subject than their teacher is. So, you know, all you math lovers out there watching this panel, you know, the teaching profession needs you.
Wonderful. And I guess just to cap things off, a more fun question here. I guess we'll go around and say your favorite number, favorite topic in math, favorite source of motivation, and just a final piece of advice for students out there. And anyone who wants to begin can start.
Could you repeat the list? Favorite number, favorite?
Favorite number, topic, source of motivation, or final piece of advice.
I can jump in if you want. So favorite number 1, you know, it's not as popularly chosen, but it's a great number. Favorite topic, this might be a little bit local because I just did a video on it, but like group theory, just like totally in love with what that can feel like in this contrast between abstract and concrete and surprisingly practical. Favorite resources or like notions of inspiration. I love the Number File podcast and just hearing from mathematicians, their like personal life experiences. I mean, we were talking earlier about how, you know, there's not a math person. Really interesting to hear from Roger Penrose how growing up he was really slow and was like failing classes because he couldn't finish his tests in time. And it was only because someone like identified, wow, you're actually doing really well on the first half of the test and you just don't get to the second half, that he was encouraged. And hearing personal stories like that, very inspiring. And they always come from very different directions. So there's avenues other than the Number File podcast, but that one I'm sort of in love with. And 4 questions is hard to remember. I've got a capacity of 3. What was the 4th?
I'm muted, sorry. Final piece of advice.
Oh, yeah. Okay, one thing I wish I had known when I was going into like college or even earlier, choose the topics to study based on who's teaching it, not what the topic is. So like get a survey for which teachers or professors or authors or whatever it might be you resonate with, and then choose the books that you read or the classes that you take or the people you engage with based on like the person you resonate with, even if it's a topic you don't think you're interested in the first place, because you're going to have a much better experience in a different topic with someone who's as enthusiastic as Art is when he talks about anything than you will with what you think you already like, and a much more uninspiring educator. And that no one seems to tell you that, but it actually, like, that's the one thing I wish I had known much earlier in life.
I'll just jump in because I do have the 4 questions in my head, and I feel like if I wait any longer, I'll forget. So my favorite number is E. My favorite subject is topology, and that's a subject that I had no idea about until I actually went to grad school. My first year of grad school, I went to a small liberal arts college, and topology was not offered. So when I went to graduate school and took the first course in topology, I completely just fell in love. It was like, the doors opened for me. And favorite resource, this is like an old-fashioned idea, but it's just like my favorite books. I really like Hatcher's topology book. It's free and downloadable online, so I love any like free book. And oh no, I said I was going to remember. Oh, last piece of advice is if you are getting something less than encouraging from a particular professor, or hopefully it wouldn't be a mentor in your life that's giving you advice that's not lifting you up, not pushing you forward, not encouraging you to continue. I would say if you have someone like that in your life, please find another source of advice. So just find that person who is going to lift you up, who's going to push you, who's going to say you can do it. Those people are out there. That's your mentor. Get a mentor. I still have mentors at this point in my life right now. Mentors are great for any age, in any stage of life that you're in. So I would just encourage you to find someone who you can talk to, who gets you and who's going to encourage you.
So my, let's see, when I was young, my favorite number was 2,520. Let's see if someone could figure out why I liked that number so much when I was a kid who loved numbers. And I'll get to it at the end. My favorite group of numbers is the Fibonacci numbers. I just think that you could spend your life discovering fun, beautiful patterns having to do with the Fibonacci numbers. But of course, I'm a big fan of E and pi and the golden ratio as well. Resources, number file, Mathologer, and of course 3 Blue 1 Brown. I mean, they're just great. So many things out there that I didn't have available to me when I was falling in love with math. Anybody get the 2,520? I saw people staring up into space. It was someone's got it. It's the smallest number that's divisible by all the numbers from 1 through 10. So as a kid, I liked sort of confirming that in my head. Like, I couldn't find a small, a smaller one, and I was, excited by that number. I guess if I were to end on a soundbite, it would be that math is not just solving for X; it's also figuring out Y.
That's very touching. My favorite number, Grant stole, it's 1 or 0, because it was a revelation to me that they act as the same sort of thing in a group. So yeah, that was exciting. My favorite subject is linear algebra because it was like the first math subject that I realized you could just see. And I remember my teacher getting some pieces of paper and being like, oh yeah, and these planes don't intersect. And then that's why there's no solution to this equation, this system of equations, which was really cool. I don't remember the third question. The final question, final piece of advice would be, well, this is terrible advice, if you're trying to do well in tests, but my piece of advice would be get obsessed with something in maths. I think that's a really great way in, just get really obsessed with a topic that you think is cool and pursue it, even though it won't help you in anything, because ages later, you'll realize that the skills that you learned in that, and maybe even the topic itself, turns out to be useful. It's really cool.
Awesome. So thank you guys so much for the comments there. And I think with that, we'll conclude our discussion. As we saw today, math communication is undoubtedly an incredibly important topic with a great amount of nuance to it. And it was an absolute pleasure exploring a bit of it with you all today. Thank you, panelists, for your time and incredible insights. And thank you to our audience for making this an especially lively discussion. We'll be sending out a follow-up email with the link shared today, as well as with the recording of the panel. We hope you enjoyed the discussion, and we'll explore and take inspiration from some of the avenues discussed today of conveying math to broader audiences. Thank you again for joining us, and thank you, panelists, for your time and support. It was truly a pleasure hearing from you all. And you're free to end the call whenever, and have a great rest of your day.
Thank you, Maya.
Thank you, Maya. Thank you.
All right, thank you, guys.
Thanks for such thoughtful questions.